Okay, F 721. This class had actually been on the books for a very long time, like since before I got here, and no one was teaching it. And I saw it in the course catalog, and I looked at uh, the description, and had a lot of things I thought should be taught. Like basically numerical methods for PDEs, spectral methods, finite difference methods, etc. And I found it rather strange that we weren't running this class because we have several faculty in mathematics in this department who was specialized for research in numerical methods for PDEs. I thought, well, we should have a class on that. And so in 2017, I dusted it off and ran it. Sorry, it's really weird. I'm seeing myself here in a screen recording this, and it's showing me the transcript. It's recording me somewhat accurately, except when I say PDE, it said PDS. So, and I don't like seeing my words pop up on the screen in front of me, but it doesn't seem to give me a way to get rid of that. It's kind of unnerving, to be honest. So, okay, I'll figure that out later. But anyway, so this is an introductory class for numerical methods for PDEs. I'm actually going to start with the non-numerical aspect of PDEs, certain basic facts about them, certain things you may remember, for instance, for a class from a PDE course such as our own Math 417, 517, and then we dive into the numerical methods, finite difference methods, spectral methods, certain tools from numerical linear algebra that are used in numerical methods, and also methods for time stepping for ODEs, since it makes sense to take a PDE that involves both space and time and decompose it into ODEs and ODE in space, ODE in time. You're familiar with that idea from separation of variables, but here we use it in a different sense, that we take a continuous PDE and we discretize it only in space. That gives us a system of ODEs. Then we can discretize that and solve that by a numerical method to approximately solve the PDE. Because this is a numerical methods class, it will be mostly MATLAB. So if coding is not your thing, you might want to run for the hills. But you probably figured that that's going to be part of this class anyway. Now, what's that beeping noise? Oh, right. Structure and technology into the mix. That's what's going. And now that's going to be on YouTube. But yeah, that's okay. He's stepping down structure anyway. So last year when I taught this class, I was in that room, and in that room was Dr. Cole, I think, teaching modern algebra. Yeah, and it was so loud. And so I closed the door, and that isn't helping me this time. So, so hopefully he figures things out soon. Otherwise, I'm just going to go across the hall and go, boop, boop. Okay, anyhow, so what am I going to have you doing in this class? Like the actual coursework, so you can think of this as a synopsis of the syllabus. So there are going to be some homework problems, not very many. In previous instances of this course, there were literally 7 problems that were assigned all semester long. Now, it doesn't sound like a lot, but remember, they involve MATLAB, or almost all of them do. And they tend to have like multiple parts. So it's still something that's fairly time consuming. I'm planning to add 1 or 2 more at the end of a semester, but I have not composed yet because one of the things that this class has been lacking in the previous times was I would discuss time stepping methods for ODEs to help solve time dependent PDEs, but I did not give any problems on them. but I will this time. So we're talking 89 problems broken down into 4 assignments. The first one won't be due for a while, so you have time to get your feet wet. The very first homework problem does not involve MATLAB, but all others will. Okay, if you really are attached to programming in another language, you can do that too. But MATLAB would probably be the easiest one to use. And then the other, so all of that is going to be 70% of the grade. The other 30% comes from comprehensive oral final exam. So we take like 45 minutes to an hour, and ask questions that come from basically inspired by the notes. And I don't know if all of you have done that with me in any class of mine before. I know you have, Megan, or have you ever I don't think you have, and yeah, so, okay. So only you know what that's like, so, and the rest of you will find out. But I'll certainly give more guidance on that towards the end of the semester. So that's something that'll happen like during what was it? Based on your preference, either during the last week of classes or during finals week. Okay. All right. So what I'm doing today, I don't have many notes here, so I might not really consume the whole hour and 15 minutes. Which is weird because for my other class, the other class I'm teaching is Math 415, 515, which is a second ODE class, and I have 7 pages of notes for that. And so I'm not sure what I was thinking, but I can, as some or maybe all of you may know, I can yammer for a long time about just about anything. Okay, so so I should mention the external fourth website, as in not Canvas, but there's a link to it on the Canvas homepage. So you've seen my course websites that are under my own website before. It's that sort of thing. So again, you get the link from Canvas. That has all the notes, and you can get them on so there's a link to the left, and one of them is resources. So you can go there and
Book 721.
yes, yeah, book 721. That's a PDF of 50 pages or so that has all the notes. So I'm just going to go through that. I will likely add some things to it toward the end on time stepping methods, but that's so you can have that in front of you if you want. And if I end up talking about something here during class that's not in the notes, like for instance, based on some question that's asked, I will include those in notes that get posted on Canvas, which are just excerpts from the main document, and also update the document as a whole. And it's still raining. Okay, not terribly heavily. Okay, so I want to make you aware of that. Also, some coding problems will involve. It'll be helpful to have certain functions, like functions for making Lagrange polynomials or making finite difference schemes. So that code will be either already posted on Canvas or posted on this site. So I'll make sure that's available to you when you need it. Okay. So what I'll be doing for time being, starting in the first chapter, there are, I think, 5 chapters in the notes. Looking at fundamental concepts related to PDEs. In general, it's not really about numerical methods yet. Okay. Okay. So, the kind of problem that we will consider has multiple parts to it. There's going to be some partial differential equation, which I'll define rigorously in a bit. But a PDE has to be associated with the domain, which I'll refer to as omega, 1 to Rn. And certainly for partial differential equations, we're looking at n greater than 1, as opposed to an ordinary differential equation, which is a solution depending on only one variable. And then you're going to have boundary conditions of some kind. And I don't know if you've seen this notation before, where I have, this is actually a symbol from a partial derivative, but when it's used in this context, partial of domain omega, that refers to the boundary of omega. So that's an important notation to get used to. Okay. Now, at this point, I'm not assuming anything about what the n independent variables mean. Do they refer to spatial coordinates? Do they refer to time? It just depends on the problem. So, and I'll frequently abbreviate boundary conditions as BCs, because I'm lazy and don't like to write very much. And it was problematic being a teacher, but whatever. Okay. Now, boundary conditions, though, could be referred to as initial conditions. Or abbreviated as IC, if one of your variables refers to time. And we'll be seeing both time-dependent and time-independent problems. Okay. But so for now, and it's speaking in very general terms, boundary conditions could apply to both space or time. Okay. So before I get into general definitions, oh, dang it. I'll give an example. Okay. Let's suppose our PDE is du dt minus second derivative with respect to x equals 0. That is known as the heat equation. And I'll specify the domain to be from 0 to 1 in space. So we're on a bounded domain in space, but also 0 to infinity in time. So then, if this is the domain omega, then the boundary of omega, which I'm calling gamma, this is conventional to refer to use gamma, uppercase gamma to refer to a boundary. So in this example, the boundary consists of a couple sets. First, we have x equals 0 and x equals 1. So just a set consisting of these two x values, but then you must account for time. So we Cartesian product that with the entire time domain. So here's our spatial boundaries. And then we have to include the entire spatial domain with the boundary in time, which just consists only of t equals 0. So all of this together is the boundary of our domain in Mega. So, and in descriptions of these sets, these Cartesian products, it's always x and t. So here's the x part, here's the t part, x part, t part. I'll just label that here. Okay. So that means our boundary conditions will be imposed on the solution u at x equals 0 and for all t, and x equals 1 and all t. So that covers the first set in our union. Whereas we'll specify an initial condition so any x in a spatial domain and then t equals 0. So, and you could think of all these boundary conditions, but because we know that our second variable refers to time, it's easier to follow if you call that the initial condition. Okay. But one way or another, the entire boundary needs to be accounted for. Questions about notation or anything like that? Okay. One thing I want to remember to do is as I fill up the board, take a picture of a make sure my notes and everything. You know, I did this all last year. Did not occur to me until just now. Since I'm recording this, I could just take a screenshot from the recording later, but oh well. It's weird to have fresh erasers and chalk. Like, wow, we actually spent some money in these classrooms. Which would nice to use have more money to pay our graduate assistants with, but no, we have gold walls. All right, I better shut up now. Okay, now, so some additional notation I'll define now. Okay. We use the capital D to refer to a very general differentiation operator. So when we apply D to U, it produces all possible first partial derivatives. So applied to a function U, what we get is a vector quantity, a vector consisting of all those first partials. And that is referred to as the gradient. Also written as this upside down delta applied to U. And then the general second derivative applied to U is going to be matrix consisting of all possible second partial derivatives. So here's derivative of U, second derivative of U with respect to x1 twice, x2 twice, so forth down the diagonal. And then the off diagonal entries will have mixed partial derivatives. Now, generally speaking, if all the second partial derivatives are continuous, then mixed partial derivatives are equal. So it's ends up being a symmetric matrix. All right. And actually, who can tell me what is the name for this? The Hessian. Okay. And we can generalize from there. So du is a vector, d squared u is a matrix. Higher order derivatives would be higher order tensors, which I won't get into. It's difficult to write on the board. But I'm going to use this to define PDEs that are as general as possible. And from there, we can get to classifying them. Okay. So, a kth order PDE is an equation of this form. We have some function f that is a function of kth order differentiation of u, and then all lower order derivatives, and so on, all the way down to du, and then just u itself, and also x. There could be other functions of x included in the equation. Equals 0, and x is in whatever domain omega that you have. Okay, and so for some arbitrary given function of all of these variables. Okay, and then u is the unknown. That is the solution of the PDE. So this an equation of this form where f could be any function of these arguments. So there are k plus 2 arguments altogether, which are themselves vectors, matrices, tensors, etc. Is a PDE. Okay. All right. Now, I wanted to introduce a notation that's helpful for describing PDEs, because PDEs always depend on more than one independent variable. That's called a multi-index. So a multi-index of order k is a tuple consisting of n non-negative integers that describe possible orders of differentiation with respect, partial differentiation with respect to different variables. So this would indicate differentiation with respect to x1 alpha 1 times. Yes.
I'm not clear with the last part of the statement. U solutions.
Oh, I'm saying that U refers to the solution of a PDE.
Oh, okay. Okay.
This is how we're labeling things. Okay, now I'm indicate. These are non-negative integers. Okay. Ultra question? And by order, so that is the sum of all of the alpha values. Okay, and this absolute value notation, which seems kind of weird in the setting, but I'm writing this here because this notation used to refer to this sum. All right. So here's some examples of multi-indices. One that'll come up very often, and differentiation operator is Laplacian. So which is often as delta U, also written as gradient symbol squared times U. And that is because it's literally equal to the divergence of the gradient of U. So in 3 dimensions, that would be uxx plus uyy plus uzz. So in general, it's the sum of all second partial derivatives that are with respect to the same variable twice. So this is 3D. But if I wanted to express Laplacian using multi-indices, I just realized I have a mistake in my notes that I'll correct later. Okay. So how to express uxx is D with the appropriate multi-index. So because I'm in 3 dimensions, every multi-index I include here has to have tuples of 3 elements. First element corresponds to x, second element for y, the third element for z. So I'd have 2, 0, 0, because we're differentiating with respect to x twice and not with respect to any other variable. And then for derivative with respect to y, so no differentiation with respect to x, twice with respect to y, nothing with respect to z. And then finally for u, z, z, I have 0, 0, 2. So those 3 differentiation operators, those multi-indices cover all the differentiation that's happening. And what I forgot to include in the notes is that all of that has to be applied to u. So all of the multi-indices that you see here are of order 2, because if you sum the elements of each tuple, you get 2. So this is a second order differentiation operator. Now, in this case, all 3 of these have the same order. If there had been different orders, you take the largest one, and you say that's the order of the whole thing.
What do you mean?
Like, suppose I had, well,
3 times with x or if the order.
yes, yeah. Now we'll come into play when I define certain categories of PDEs in a bit. Okay. Other examples. So for uxy, if we're in 2 dimensions, that'd be d1, 1. Still, so now we're only differentiating once with respect to each variable once, but because it's both variables, this is still a second order operator just from summing the elements of a tuple. That's second order. Most PDEs we'll deal with will be second order. But when it's not, there's an equation that I'll write later called the beam equation that includes a 4th derivative with respect to x. And in the beam equation, we're using a 4th order multi-index, 4, 0. The reason for the comma 0 is because this is from a beam equation that depends on both x and t. So whatever multi-indices you include, they should have two elements. One for differentiation with respect to x, the other with respect to t. So this is for a beam equation, which is ut equals minus ux x x x. Okay. Wait. That is the wrong equation. One. I know I have it here somewhere. It's actually be UTT. Yeah. So UTT, that would have a multi-index of 0, 2. So we have a second order differentiation operator on the left side, fourth order right side, the PDE as a whole is fourth order. Questions about multi-index notation? Oh, probably said they moved up 33 minutes so far. And look at like how I get from these notes in like half an hour. It's like, well, no. Okay. I could even fall behind. Okay. All right, now, actually, have all of you taken 417 or 517? You did.
I did not.
Okay, but you take some introductory PDE class, hopefully. Okay. Did you?
Long time ago.
Oh, okay. Oh, okay. In where?
In bachelor's.
Oh, right. Okay. All right. So in a class like that, you would deal almost exclusively with linear PDEs, and most of the time we'll be dealing with that too. But I'll give a whole hierarchy of how we classify PDEs, because it's not just a matter of linear and nonlinear. There's classifications in between, which depends how we go about solving.
But I could use the brochure.
Oh, that's what the first part of this semester is about. It's all the first chapter of the notes.
Your channel has the 417.
What?
Your channel has 417.
Oh, yeah. Well, and I've been recording my lectures for several years now, but I feel bad for any student who feels the need to watch them, because there are times where I will watch myself like to check up on something, and it's like, oh my God, this is painful. Okay. Not good TV. So, although the very first time I was recorded, it wasn't by me. In my first year here, I was teaching multivariable calculus. Yeah, this is how I fall behind. And a student asked to record me, I guess for his own purposes. I was like, okay, fine, I don't care. And then he would post it on YouTube for the other students. But what he did though, because this is like an hour and 15-minute class, so a video file would be pretty large. And back then, this is back in 2010, so I think it's harder to upload large videos to YouTube back then. So what he did is, anytime I paused at all, he would edit that out. So you can see me at super speed pretty much, like through all that stuff. And it's still there. You can find it on my channel. So like Math 280 from 2010, and you'll find these Gish lectures. Okay, so all right, so first we have the nicest case linear. So it's a PDE of this form, where we have sum over all multi-indices of order less than or equal to k. So k is used to refer to the order of the PDE, so highest order differentiation you can get. And then we'll have some coefficient, so for each multi-index, we'll have a coefficient as a function of only x, that's very important, only x, times a derivative with that multi-index applied to u. And all of that is equal to the function f, and it also depends only on x. So PDE has to be of this form to be considered linear. The functions alpha of x are referred to as coefficients. The function f is often referred to as a source term. And if f equals 0, then PDE is said to be homogeneous. Because in that case, u equals 0 would be a trivial solution. Assuming that whatever initial boundary conditions you have are also homogeneous. Okay. Now, we'll generalize just a little bit. Second type is semilinear. Okay, so the really the only difference is in the source term compared to a linear equation. So we have this first part that's exactly the same as for linear case. Whoops, it should be a alpha x, so coefficients depending only on x. And then you have a final term here called f0, and that could depend on pretty much anything. Derivatives of u, but notice only up to order k minus 1. So you cannot have the highest order derivative, order k, included here.
What happens if
If it was, then that would be a different kind of PDE. It just can't be classified. So you can have a PDE of that form, you just can't call it semilinear. Depends on du, u, x, 0. Okay. All right. So then, now I'll change the first part of the PDE to get the next category. It's quasi-linear. So what happens now is the coefficients are allowed to depend on same things that the source term could before. So it can be a function of derivatives of u up to order k minus 1 again. All right, so all of this times the alpha of u. So the only time you can see a kth order derivative is right in here. Okay, and then the source term is the same as in the quasi-linear case, or semilinear case. In a first PDE course like 517, one type of equation, certainly came up in that class, and usually in an introductory class, would be a quasi-linear first order PDE, and you can solve using what's called a method of characteristics. So it's usually the first time a student sees anything like that. And then finally, we have what's called fully nonlinear. So these two are still nonlinear, but we have these more specific adjectives for them. But any PDE that doesn't fall into any of these three baskets is called fully nonlinear. Right. Now, everything I've described so far is for a single equation where a function u and its derivatives are, or where partial derivatives are scalar valued. A system of PDEs now, the form of a general system of PDEs, it turns out what I'm writing here is exactly the same as when I wrote the most general PDE earlier. Okay. The difference is that the solution u and the function f that defines the system PDEs have to be both vector values. Okay. So u is a function that takes in n independent variables as inputs, but produces m dependent variables as outputs. So the u goes from Rn to Rm. And f also produces vectors in Rm. Usually n equals m. Don't want to say that's always the case, but what?
No, I'm just thinking
Oh, okay.
it goes from n-dimensional vector space to
Yes. Yeah. Okay. And you may recall from from an ODE class that if you have any higher order ODE, it can be rewritten as a system of first order ODEs, and sometimes it's done with PDEs that we work with a lower order system to solve. And a lot of numerical methods that may be designed with a single PDE in mind can be generalized, hopefully in a straightforward manner, to systems. Any questions up to this point? Okay. Actually, all I have for the remainder of the time are a whole bunch of examples of PDEs, including ones that we'll be spending a lot of time on in the assignments. I'll Okay. Okay. The first is called a linear advection. Convection equation. And that is ut plus ux is equal to 0. And the general solution be a function of this form. Okay. Yeah, it's a function f of x minus t. So if you set t equals 0, that would be the initial data. And then as t increases, the graph of f is transformed. What kind of graph transformation is this?
You mean?
Like, if you know the graph of f of x, then how does the graph of f of x minus t relate to the graph of f of x? I don't know if this comes up in Math 101 or. I know I've dealt with graph transformations in a while.
Is it to do with the stretch of the
Not that. That's a different graph transformation.
translation?
Yes. What kind?
If we add on the success, so it should move up to right.
Yes, this is shifting to the right by t units. And so you think of it as propagation to the right with a speed of 1, because as the amount of time t passes, well, graph of f is shifted by t units. Whereas if I changes to a minus, then that's going to shift to the left. The general solution would be f of x plus t. So an advective equation like this one describes propagation, like so certain wave equations where you have waves propagating in a certain direction. This often happens when you have the order of time derivative and space derivative being equal. Okay. Next, certainly see this one. The equation ut equals uxx. So this models diffusion. So intuitively, if you have a heat source, then over time, that heat source will raise the temperature in its surroundings, eventually converging to a uniform temperature. There's no other effect at play. So we have heat energy diffusing throughout the spatial domain. Now, one thing I want to mention is a unusual application of this kind of diffusion equation, where that comes from image processing, and so one of my research projects has been about this, because this equation describes smoothing. Solutions of a heat equation tend to be smooth, even if the initial temperature profile is highly discontinuous, has like jumps in it, for instance. Over time, it will smooth out, like eventually to a constant. So now suppose you have an image, and you treat its pixel values, like for simplicity, I'll describe a grayscale image. So it has pixel values from 0 for black to 255 for white, and a bunch of different shades in between. So if you treat your given image as a temperature profile, initial temperature profile, suppose the image has noise, fuzziness, which would be tiny fluctuations in the pixel values. Then, if you provide that initial data to a diffusive equation like this one, then those little variations will smooth out. It will remove the noise. Now, you have to be careful about, because not everything on the image is noise. There are going to be other things like edges, details that you want to keep. And if anything, you'd like to sharpen those. So in that case, you perform what is called backwards diffusion, which is nothing more than diffusion run in reverse, and that would be manifested here by changing this equation to ut equals minus uxx. So instead of smoothing, you have the opposite. So smoothing is manifests itself through exponential decay in the solution. Running backwards in time is exponential growth. So what I actually have worked with is a PDE where it's not just a heat equation, you have some coefficient here that is positive in away from edges where you want the smoothing to occur, and negative near edges, so to have the opposite effect, sharpening them. It's called the Perron-Malik equation. That's relatively new. It was developed in 1990. And I worked with certain variations of that for enhancing images in various ways, or sharpening, or what's called denoising. Okay. So you never know, like if you have some effect you want to achieve, like advection or diffusion, then you can go ahead and feed it to whatever PDE models that effect, even if that PDE is generally used to model very different phenomena. Okay, here we have these effects put together. A convection diffusion equation. WT plus CUX equals DUXX. Capital D here is not meant to convey differentiation like before, it's just a coefficient. So the UX term is for the convection part. So there's movement, propagation. The UXX, like in the heat equation, is the diffusion part. So, yeah.
Before UXX,
Oh,
UXX was the diffusion part?
yes, just like in this equation. So this equation, we have only diffusion, but here we have only advection. Here we have both effects. In addition, if I were to have a term that is just a coefficient times u, so no derivative, just plain old u, that's a reaction term. So you could have like a advection, diffusion, reaction equation that has all three. So UXX, UX, and U. Some of my research has been on reaction diffusion equations that doesn't have a UX term, but it has a UXX and a U. All right. This is one to be dealing with a lot. Okay, well, a whole lot of time left, but okay. UXX is equal to F. This is called Poisson's equation. Majority of the homework problems that you will have in this course will feature Poisson's equation, the relatively simple PDE you work with for numerical methods. Okay. And this is in 1D. Or in general, Laplacian of u is equal to f. And however many spatial dimensions you have. I should mention this equation is often written with a minus on the left side, like minus uxx equals f. That doesn't really matter because that's equivalent to uxx equals minus f, because f can be anything. But it's because the second derivative operator has negative eigenvalues. So we write it as minus uxx, then they become positive. Poisson's equation is used to model electrostatic potential. Okay. So here we have a time-independent PDE. So you would not have an initial condition, but you would have boundary conditions. If f is 0, that is called Laplacian's equation. Talk more about that in a later class. Questions about any of these? A number more examples to go. So try not to yammer too much about each one. A particular one. Each one. Okay. Berger's equation. And you might who's credit to is Berger's, not Berger. I don't know if you were telling me about one of my papers, so it's a little embarrassing. Okay, so this is so all the PDs I've given examples of so far, those have been linear. Here's one that's quasi-linear. So we have 1/2 u squared. So we take a derivative of u squared with respect to x. So the u squared with respect to x. The u squared makes it nonlinear. Now another way of writing that is ut plus ux equals 0. It's by carrying out the differentiation of a 1/2 u squared. So we see the ux has a coefficient that depends on u. That's why it is not a linear equation. One reason for writing it in this form is it's a typical way of expressing what's called a conservation law, which is an equation in form ut plus some function f of u, the whole thing with respect to x, equals 0. You may remember that PDEs are generally derived from conservation relations, conservation of mass, conservation of energy. So these fundamental equations, heat equation, wave equation, and so forth, you start with some physical law expressed as an equation, usually involving integrals. And through certain manipulations for multivariable calculus, you wind up with the PDE itself. Here's a semilinear PDE. So we have this Laplacian on the left side. We have a nonlinear function of u on the right side, u squared. That's what makes it semilinear. So linear on the left, but something nonlinear on the right, semilinear. wave equation. It's something we've seen in a first course in PDEs, UTT equals UXX. So this features waves that are propagating to the left and right. Unlike the first order convection equation from before, but only in propagation in one direction. And you can express this as a system involving two quantities, u and v, derivative with respect to t, equals a matrix 0, 1, 1, 0 times uv again with respect to x. So this is a system of two first-order linear PDEs. If I were to carry out the matrix vector multiplication, that would give me ut equals vx, vt equals ux. And to see how this is equivalent to the other form of a wave equation, if I take the first equation and differentiate both sides with respect to t, I get utt equals cxt. Then I differentiate the second equation with respect to x. vtx equals uxx. But here we have mixed second partial derivatives that are equal. So ut equals uxx. Here's a rather unusual PDE called the KdV equation. Well, full name is written in notes, but it's often referred to as KdV because people don't want to write it out. This is third order, so we have ut plus ux. So it starts out looking like Berger's equation. But then on the right side, we have the coefficient epsilon times uxxx. What's unusual about this kind of equation, it's nonlinear and third order. Generally, those kind of equations are impossible to solve analytically. But it turns out analytical solutions are known for a KdV equation, and the solutions are called solitons. Solitons are very unusual in that if you were to graph a solution of the KdV equation over time, you would see these solitons, these are waves propagating towards each other. They will collide and pass through each other with no disturbance. So it's kind of weird that they collide and remain intact and just keep going on their merry way. So it's a very unusual equation indeed to have the properties intact. What is falling behind? Or, oh, why am I recording the video? I really don't want to be doing that. Okay. Have we recorded a video all this time? No, okay. What happened there? The question about anything you've seen here. Few examples to go for complicated problems. What was the number of the last equation?
It's
8, okay. All right, in my notes, I don't have them numbered, so. Um,
No, but you wrote this one separately. The equation.
oh, okay, yeah. Okay.
Sorry.
Incompressible Navier-Stokes. Navier-Stokes equations are one of those equations that offer $1 million prize if one could solve. I mean, analytically. We have the U is a vector valued quantity, ut plus u dot gradient equals minus gradient of p means pressure, u is velocity, plus coefficient, Greek letter nu. Then we have this additional equation. This one makes it incompressible. The divergence of a vector field u must be 0. But divergence, the physical interpretation of divergence is a tendency of a velocity field to diverge from whatever point you're taking the divergence at. If it diverges to 0, that means it's not going to diverge at all. So that's why a fluid that satisfies this equation here is incompressible. So if you remove this, then it is the compressible Navier-Stokes. Okay. And this is called a DAE, differential algebraic equation. Whereas the compressible Navier-Stokes is just an ordinary system of PDEs. One of my PhD students did some work on applying a numerical method of mine to compressible Navier-Stokes. Pretty nasty problem. So this is one of the most important equations in fluid dynamics. And so pretty much any fluid dynamics problem that comes up, what are PDEs, probably related in some way to Navier-Stokes. Water equation. Okay, so we have P plus Hx. UU actually gives them the first part of Berger's equation again, but different right-hand side. X. See, this equation is written in conservation law form. We have ht plus a function of h with respect to x is 0. This, although it's not written in conservation law, could be rewritten to be in that form. So this is a system of conservation laws. So again, it's still modeling fluid dynamics, but this time in the case of shallow water. And then the last example, called the iconal equation. So this is fully nonlinear. So the magnitude of the gradient must be equal to 1. So this would be the square root of ux squared plus uy squared plus uc squared, and it's equal to 1. So definitely does not fall into the linear, semilinear, quasi linear category. So it's fully nonlinear. All right, so these are just a small sample of well-known, often worked on PDEs that are out there, but it's a fairly representative sample kind of things you see in the literature. Now, in this class, we're going to keep things pretty simple, but the numerical methods that you learn and apply to those simple equations prepare you pretty well for working on these more complicated ones too. what we're doing in upcoming classes is focusing on certain PDEs in particular, heat equation, wave equation, Laplace equation, and certain things that are known about their solutions, which will be taken into account when we design numerical methods for it. And also what it means for a problem to be well posed, because I mentioned a heat equation, where the solution smooths out over time. If you run the heat equation backwards in time, then it leads to exponential growth. Well, that's something that isn't really physical. And can you imagine some sort of natural phenomenon that exhibit exponential growth? Well, okay, we have that population, and exponential population growth is a problem, or eventually becomes one. So you want to have problems that model situations that can occur in nature, and that leads to the concept of what's called a well-posed problem, which I'll formalize on Thursday. Okay, so that's all for today, and we'll just keep on going. So later after class, or actually after my other class, what I'll do is I'll post the recording and also post notes, especially if I have to make any changes to them, because I get some mistakes or things like that. So that'll always show up in a discussion item in Canvas each time. Okay.